Hello, it's Keith here, and this is lesson 4 of my 68,000 assembly programming tutorials. Now, we've been looking at various commands over the last couple of lessons, but we've still got an awful lot of stuff to go before we can really say we know the majority of the commands we're going to need. And one of the really serious things that I've missed mentioning so far is the stack. Now, what is the stack? Well, it's not so important with 68,000 programming as with systems with less registers like the Z80 or the 6502, but the stack is a temporary store. In many times in programming, we'll need to back up our registers so we can use them in a subprogram, and we'll want to restore the original values when the subprogram ends and things like that. So the stack is a temporary location where we can put data into and then get it back later on. So how does the stack work? Well, the clue is in the name, because the stack is basically a pile, and if you think of it like a in tray and you've got some papers in that in tray, that's a fairly good way of thinking about it, because the important thing about the stack is the order which you take data out of it and put data into it. And the order is that the last item you put on the stack is the first item you take off. So if you imagine you've got your in tray and you put in 10 items, you can't go riffling through and pull out the middle item. You have to take them off in the order that you put them on, at least generally speaking. And so if you have a look at this example I've got here on screen, we've got an imaginary stack here marked by the stack pointer, and if we want to put this item onto the stack, that item will then appear at the top of the stack here. And then if we want to put another item onto the stack, you'll see it appears again above the previous item, and then when we take those items off, they come out in the reverse order. Now, the fact that they come out in the reverse order is important because obviously if we're pushing on values from particular registers, like say we're backing up register D0 and then D1, we'll need to pull them off in the opposite order. We'll see a lot of examples of that later, so don't worry about it too much if you don't understand it. Anyway, what about these stack commands? Well, on the Z80 we have the push and pop commands. On the 6502 we have the push and pull commands. Now, rather obscurely, on the 68,000 we don't have any named commands like that, and that might seem like a disadvantage, but it really isn't, because the ironic thing about the 68,000 is we have these special addressing modes that work as a stack. So whenever we specify an address register in brackets with a minus before it, we're effectively pushing onto the stack. And whenever we have a plus at the end of an address register in brackets, we're effectively popping an item off the stack. And the reason for that is that the stack grows backwards in memory, so that every time we put an item onto the stack pointer goes down, and every time we pop one off, the stack pointer goes up. Now, don't worry if you don't quite understand that yet, because we're going to be looking at some examples. The other thing to understand, as I've mentioned before, is that the address register A7 is the stack pointer. Now, we can use SP or A7 in our code and it will work exactly the same because the assembler is converting between the two, but that's just something to understand when we talk about the stack pointer. Now, you can use other registers as stack pointers. There is a slight trick that they don't work the same in one case. We will explain that later, but generally speaking, if you want a temporary stack pointer or you want to treat another address register as a stack, you can do that. That's just fine. So that's a brief introduction to the stack, but I think it's going to become much clearer what it does when we actually see it in use. So we're going to run an example here, and then I'm going to talk through the code and we're going to see what it does. Okay, so here we've got an example running on the Genesis, and we're using the stack pointer or address register 7 because remember they are the same thing. And what we're doing is we're setting a fixed memory location as our stack pointer temporarily. Now, this isn't generally a good idea, but we're doing this for testing purposes, and the reason we're doing that is so we can clearly see that memory, because we're dumping the memory that is the stack pointer to the screen so we can see the stack as it appears in memory. And then what we're going to do is we're going to start pushing some values onto the stack, and we're going to see how that is affected. So here's the stack pointer at the start of our example. We've set the stack pointer, register A7 here, to FFO100. You can see that here. And FFO100 is effectively the end of this memory here. So our stack pointer is basically pointing here at the moment. And if you want another demonstration of this, I've actually drawn this pink blob on my website here so that you can see this potentially more clearly. So if you're not clear on this after watching this video, please go and have a look at the website and maybe that'll help as well. But anyway, at this first example, our stack pointer is effectively at the end of this memory range here. Now, what are we going to do first? Well, what we're going to do is we're going to move a word, that's 2 bytes, and the bytes are going to be 1, 2, 3, 4, and we're going to push those onto the stack. So because of this minus here, the stack pointer is decremented by the amount we're pushing before the data is written to memory. And remember, this could be A7 in brackets here and it would work exactly the same. So we're going to push 2 bytes onto the stack. So you can see our stack pointer has gone down to FE here, and you can see here the 2 bytes have been pushed onto the stack. And because this is a big endian system, the 1, 2, the top byte is on the left hand side and the 3, 4 is on the right hand side. I say that because on the Z80 they'd be the other way round. But we're not using the Z80, this is a big endian system. And the current stack pointer is FE, which is effectively this position here. So that's what happens when we push a word on, 2 bytes. Well, what happens if we push on a long, or a long word as it's sometimes called? That's 4 bytes. And so once again, we've got this minus here before the stack pointer, so the stack pointer is going to be decremented by 4 bytes, and then this data here is going to be put into that new position. So our stack pointer was here, and now it has been pushed back 4 bytes to here, and you can see here we've got those 4 bytes. And again, you can see the stack pointer has changed here. So that's what happens when we push a long onto this stack. The stack is affected by 4 bytes and the 4 bytes are pushed on. So what happens if we push a single byte onto the stack? Well, this might catch you out. You can see here we've pushed on the value 96 twice. Why have we put it on twice? Well, I just wanted to make a point. So at the end of the last command, the stack pointer was here, and we've pushed a single byte on. So you would expect the stack pointer to have moved by 2 bytes, but it's actually moved by 4. You can see the 96 we pushed on here and the 96 we pushed on here, but we've got 2 junk bytes here, EC and 00. When we've pushed the single byte onto the stack pointer, it's actually moved by 2 bytes. Now why is this? Well, I said you could use any register from A0 to A7 as a stack pointer, but the A7 and SP are the official stack pointer. And A7 and SP work differently when we move a byte onto the stack with the pre-decrement here. And what happens is it moves by 2 bytes. Any other register, if we'd have used A6 here, it would have moved just by a single byte. And the reason for this is that if you remember, the 68,000 can only address words and long words at even byte alignments. And because the stack pointer is designed to work in a combination of bytes, words and longs, that wouldn't work properly if we only pushed on a single byte. So when we push on a single byte, an extra byte is padded in and it moves by 2 bytes. This of course is no negative problem when we actually come to popping the data off the stack again, so it's not something to worry about. So now we've pushed a lot of data onto the stack. Well, what about popping it off again? Well, if we want to pop data off the stack, we don't need to pop it off into the same registers. But if we want the data to come off correctly, we do need to pop it off with the same length specified. So what we're going to do now is we're going to pop off our bytes, our long and our word, and we're going to show them to the screen because we're going to pop them off into D0. So while we push them on in immediate values, we're going to pull them off into D0. The way we pull them off is to put a plus after the SP register in brackets, and that is called post increment. And so let's have a go at that and see what happens. So you can see here we've popped off 2 bytes here into the D0 register, and you can see here now that that 96 is shown to the screen, and after that you can see the stack pointer here. Then we pop off our long, and you can see FF, EE, DD, CC. Of course, we're reading these straight off the stack, and so the stack pointer would have moved from here to now here. And then we pop off our word here, and so that's our 1, 2, 3, 4 here. And you can see now that the stack pointer is now at FF0100, which is exactly the same place as it started. And that's very important if you're running this within a call in a subprogram, because you need to make sure your subprograms end at the same point as they started with regards to the stack. And we'll discuss why that is in just a moment. One important thing to notice is while we push our data onto the stack in a certain order with certain lengths of data being specified, we don't have to pull that off in the same way. We can actually specify different lengths, and we will get a result that may well be valid. Of course, that may cause problems for us, but our code, if we program it correctly, can do that, and there may be benefits to doing that. We could push 2 words onto the stack and then pull them off as a long, for example. So let's just have a look at another example here. So this time, you'll notice again that our stack pointer ends up at exactly the same place as it starts, but this time we've done something quite strange. So we've loaded off our byte, hexadecimal 96 here, and that's been read in just fine by this command here, but then we've read in a long. Now if you remember, we pushed on a byte to the stack, and because of the way the stack pointer works, there's a padded byte as well, and we've now popped off that hexadecimal 96 and that padded byte, and then we've read in the first 2 bytes of the long that we pushed onto the stack before just here. So now when we read another long in, we're actually getting the second 2 bytes, and we're getting our original word that we pushed onto the stack. So we've got some quite weird data back, and if we've done that by mistake, that could cause us a serious problem. But as I say, there may be cases where you actually want to do that intentionally. So that's something to bear in mind. And the point I'm trying to make is that the stack doesn't care. It doesn't care or know what order we push the data onto the stack, or what types of data, bytes, words or longs, get pushed onto the stack. It's an addressing mode. It's going to do what we tell it to. And if we tell it something silly, it's going to do something silly. So that's something very important to notice. But as I say, the most important thing to take away from this is we can put data onto the stack and we can get it back later. And we could do a whole range of things in between here, messing up all of the registers, and we can get those registers back later. So in that example, I did mention that if we're in a subroutine, we'll want the stack to be in the same situation at the end of the subroutine as it was at the beginning. And I didn't explain why, but of course I'm going to now. The important thing to understand is that the processor is using our stack in its own functionality when it comes to subroutines. If you think of a subroutine, what it does is it remembers the calling address, it then jumps to another address within the program, it runs some code, and then it returns back to that original address. And the important thing you need to know is that the way it remembers that original address, it doesn't have some magic registers it uses, it actually pushes them onto the stack, the exact same stack that we're using in our code. So if we're running a subprogram, we need to make sure the address register is in the same position at the end as it started. Otherwise, when it tries to return, it's going to read in some duff code and it's going to execute goodness knows what. So we're going to have to make sure we do things correctly. Otherwise, we could be in with some serious problems. So let's have a look at the stack pointer and how the JSR command affects the stack pointer. So here I've got a fairly simple routine here. We're going to again set a fake stack pointer. This is going to work well on the Genesis, but probably won't work on anything else. We're going to show the stack here. We're then going to show the stack pointer. We're then going to jump to this stack test routine. We're then going to show the stack again and the stack pointer again. We're then going to load in this address return pos, which will be the next command that will be run after the stack test subroutine. So after this RTS return, we would end up at return pos. So we're going to show that address just to make a point. And then what we're going to do is we're going to return back to here and we're going to show another dump of the stack. So we're showing the stack before, during and after a subroutine, and we'll see what actually happens. So the first good thing is we've got 3 dumps to the screen, which means we haven't crashed the processor. So what's actually happened? Well, here is the stack at the start of this example. And then you can see we've shown the stack again, and this is being shown at this point here. Now here we've dumped the return pos to screen, and you can see that the return pos is 2C8 in hexadecimal. The ROM is at very low memory addresses within the Genesis, which is why it's such a surprisingly low number. The important thing to notice is you can see this same long just here within the stack, and that's not coincidence. That's because, as I said, when we do this jump to subroutine, the following address is stored onto the stack for that return. And you can see here that the stack pointer has actually gone down from hexadecimal FFO100 to hexadecimal FFOFC. So it's gone down by 4 as this has been pushed onto the stack. When we've returned here, you can see that 2C8 has gone. The reason it's gone is this isn't a function of the return command. It doesn't delete data from the stack. But what I've been kind of keeping secret from you all along is when we've been doing these jumps to commands like the monitor, they are of course also using the stack because the jump to subroutine command uses the stack as part of its functionality. So anything above the stack pointer is going to get corrupted by the calls within my testing routines like this monitor command, and these commands will also be pushing registers onto the stack to avoid breaking things as part of their display to screen functions. So anything that's above the stack during our testing is likely to get corrupted just by our test routines, ironically. But as I say, the point I'm making here is that the stack ended up at the same place after the subroutine as before, and during the subroutine, the address of the return was stored onto the stack. Now, I said before we had to be careful pushing stuff onto the stack, so let me show you why. So let's just put a simple command in here. We're going to push an extra item onto the stack at the start of stack test, and we're not going to pop it off. So this is a very silly thing we're doing here. Let's run it and see what happens. Now you can see here that here's the stack, and you can see here is the 96 we just pushed on. Now where's that third dump of the stack here? We should have shown a third one when we returned. Well, what's actually happened is the processor's crashed. The reason for that is rather than popping this long off the stack, it's now pulled this long off the stack. So it's now tried to execute memory address 96FE0000. Well, who knows what that is? What it certainly isn't is part of our code, so the processor has crashed. Well, what should we have done? Well, it's really quite simple. We should have popped the data off the stack. If we pop the data off the stack, just popping a single byte off as we pushed on before, this will now match. And you can see we've now got that third command, and our stack pointer is the same at the start and the end, and that's what we want. Now, often in my code, I will tab indent any commands between pushes and pops, so I can make sure I do the pushes and pops in the correct order and don't make any mistakes like that. But as I say, the important thing is your stack pointer needs to be the same at the end as it was at the start. And alternatively, you do have another way you can do this. I can do move.l a7, a6, and then rather than pop off the stack, I can just do the opposite at the end. If I run this also works fine. We haven't crashed, even though we have not popped off all of the stuff we pushed onto the stack, because we actually backed up the stack pointer into A6 and restored it from A6 to A7. The processor doesn't care what you do with the stack. All it cares about is when it tries to run a return command, the address at the top of the stack is where it's going to try and return. We can even do crazy things like this. If we change the jump to subroutine here to a jump command, we're now jumping to here. And of course, because we've used just a jump, the return address hasn't been pushed onto the stack, but we can do it ourselves. We load the effective address of the return position onto A6, we then push A6 onto the stack, and we use our return command, even though we never jump to a subroutine. The processor doesn't care. It doesn't care that we started stack test with a jump. It will still pull the next thing off the stack and return to it. So because the stack is correct, this works just fine. Even though we've really done something quite odd here, and we can exploit this if we want. We can use the return command to effectively jump to an address we pushed onto the stack. So anyway, that's pretty extreme. I don't want you to worry about that if you don't understand it, but it's something that's a trick that you may want to take advantage of sometimes. You can use the return command to effectively jump to an address that you pushed onto the stack. Anyway, so the stack pointer is very helpful for us to be able to back up registers, and it's also very important to the way that the processor deals with subroutines. Now the 68000 has a command that is really amazing compared to the 8-bit we may be used to, and that is the move_n command. Now we don't want to have to worry about our registers getting corrupted while we're running subroutines, and we may want to back them up, and often we may want to back a lot of them up in one go. Now, with a Z80 or a 6502, we have to push each register one by one, or in pairs like the Z80. But with the 68000, we've got this miracle move_n command. What it does is it moves multiple registers onto the stack in a single command. And this is really, really good. So let's have a look at it and let's see it in action. So how does the move_n command work? Well, the move_n command will accept various permutations and combinations of registers, and it will push them all onto the stack and pop them all off the stack automatically for us. And this is really good for us because, as I said before, we really need to pop registers off the stack in the same order as we push them on. But if this command is doing all the work for us, then we don't really have any problems there. The other thing that's important to understand about the move command is we can specify various registers. We can specify ranges of registers, we can specify unrelated registers, and we can specify every single register. We can even back up the stack pointer onto the stack, ironically. So as I say, this is a really powerful command, and it's one that you definitely want to know about because you're going to want to use it. So what are we going to do here? Well, we're going to push on registers D0 to D2 at the word level onto the stack here, and we're going to show the stack, and then we're going to pop them off because this is the matching command here to this one here. So let's try it out. So here we've set our register to 1, 2, 3, 4, and you can see that here. We've got A, B, C, D, and you can see this one here, and we've got 9, 8, 7, 6, and you can see that one here. So it's actually pushed on D2 first, then D1, then D0. But that really doesn't matter. The important thing to understand is that the registers are being pushed onto the stack, and we can pop them off in exactly the same way. Now, if we want a consecutive numerical range of registers pushed onto the stack, we just use a minus, or a dash if you prefer to call it that, to specify the range, and we do the same when we pop it off. But we do have other options. As well as being able to use a minus, we can use unrelated registers, for example D0, D3 and D5. We can push those onto the stack with just a slash, and that of course won't push on D1, D2 or D4. And we can pop them off in exactly the same way, and we can even push on every single register by specifying D0 to D7 as a range and A0 to A7 as a range and putting a slash between them. So we can do combinations of ranges and unrelated registers if we want. So these commands are really powerful, and of course we can do these at the byte or the word or the long level if we prefer. the important thing to notice is this is kind of our superior command. This one will back up absolutely everything and restore absolutely everything. So if you want to be safe when you're creating your own subroutines, just put this command at the start and this command at the end, and that will back up everything and restore everything at the end of your command. The only thing, of course, to notice is if you wanted your command to return some kind of status value, maybe you'd want to remove one of these. So you may want to, for example, set D0 to an error level or something. So you would maybe want to just leave D0 out of that range in that case, but it just depends what you're doing. I use these an awful lot. With things like my print char command, I don't want to have any registers corrupted by that command because it makes my other programs start to play up and it makes my debugging harder. So I'll use this command quite a lot just to back and restore everything up. Of course, the only thing to bear in mind though is pushing a lot of stuff onto the stack and popping it off is going to slow things down a little bit. But at this stage, it's probably better to be safe and have code that we don't have bugs in rather than trying to squeeze out all of the speed because we're just learning things at this stage. So that's an important thing to notice. And so the movem command is definitely one you want to know about and you want to try and take advantage of when you're using the stack because it's going to save you a lot of time and probably a lot of debugging as well. Now, earlier when I was playing around with the stack, you saw me load in the address of the return label using LEA, and then I transferred that onto the stack with a move command. There is an easier way of doing it. If we want to put an address on the stack, we can use the PEA command, which stands for push effective address. This will push an address of a label that we specify onto the stack, and this is useful for us in that case where I was misusing the return command. We can do that, but also the stack is often used for storing temporary variables and passing them onto a subprogram. So if we want to specify an address to a subprogram by pushing it onto the stack, we can do that with the PEA command. So you can see here we've loaded the effective address of testadua here, which is here, and that is apparently 2CE. And then what we've done is we've pushed that address onto the stack, and then we've shown the stack contents here. And you can see here, this long here is indeed 2CE here. So we've pushed the effective address of test address onto the stack here. And the important thing to remember about LEA and PEA is they work well with relocatable code and they're going to be a lot more reliable. So I'd strongly suggest you use those whenever you're using the addresses of labels within your code. So there we go. Now that may well be a command that you think, well, I don't really understand why I'm going to need that. And it's one of those things that if you don't know why you're going to need it, you really don't need it at this stage. But just bear it in mind for the future because there will come a time where you do need it. Consider it something that's been introduced to you at this stage and that one day you will come to need it more and it will then be something you'll remember and be able to use at that time. Okay, we've been talking about the stack for a long time there, but there are some other things I want to discuss today. I want to go over a few more mathematics commands that are going to help you along as we start to learn the 68,000. The first of these is a very simple command. It's called neg. This means negative, and all it does is it converts a positive number into a negative number. Now, I've discussed before to some extent how negative numbers work in hexadecimal, and as I've said before, if you don't understand it at this stage, I do have another tutorial on YouTube that explains how they work, so please go and check that out if you're still a little bit hazy about how they work. We're going to have a look today at some examples using the negatives, so let's take a look. Just to very briefly describe it, the way a negative number works is you invert all of the bits of the positive number and you add 1, and that is effectively the negative number in hexadecimal. So if we take a hexadecimal 64, for example, and we negate it, so what we end up with is FFFFFC0 here. Let me just prove that is true by loading up the Windows calculator, which cannot lie. And if we change this to decimal, now I write in minus 64. And then I press hex, you'll see it does indeed equal FFFFCO. So at this point, if you don't understand why negative 64 is FFFFCO, please look that up yourself. But from the point of view of this command, if we want to turn positive 64 into negative 64, we can just use this neg command and that will do it. Now, like so many commands, the neg command can work at the byte, word or long level, and it will have a different effect on the resultant bits. If we're working at the word level, you see only these 2 bytes have been changed to FFs here, and that would of course have negative effect if you were doing compares at the long level later on. But as I say, the point I'm making is that you can use this command to invert things. So I'll just prove that to you. If I rem out this positive 64 here and just leave this negative 64 here, and we run this again, you can see now we started at FFFFFCO, and we've changed it to 0040 here. But again, these top bits are now kind of corrupted. So the negative command is a very easy way for us to flip a positive number to a negative number. And there will be times we need to do this. If we need to add a number, but we need the number to be negative or something, we can do that with this command. Now, a negative command is pretty unremarkable. The Z80 has one, and that's not too exciting to us. What is very exciting, though, is the 68000 has something that most 8-bits do not have. It has multiply and divide commands. It can actually do multiplication and division for us in a single command. This is amazing, so let's check it out. Now, the important thing to understand with multiplication and division on the 68000 is, as I've said before, the processor doesn't know whether a register contains a positive or negative number. That FFCO could be a very high number or a slightly low number. It just depends on the way we treat it. So the important thing is, if we're considering our register to contain an unsigned number, we have to use this mulu command, multiply unsigned. If it's a signed number, well, you need to use this mols command, multiply signed. So we're going to try this 2 times with a positive and a negative number, and we're going to see what happens. So here you can see, and we've got this 3401, and then we've multiplied it by hexadecimal 100, which effectively just moves it along 2 digits. So a very straightforward result that we can easily see here, and so there's no problem there. And you can see here again, we've multiplied it and it's moved along 2 digits here. So that's what happens when we use the mols command. But what happens if we use the mulu command instead? Well, let's try that out. Well, we've multiplied at the word level here, but we can see something's gone wrong here. The top byte here, the top 2 digits, have turned to zeros, and that's because the multiply command hasn't understood that this is a negative number. So it's actually corrupted the top 2 digits there, and that's why it's important to bear in mind whether we're doing signed or unsigned mathematics and to use the appropriate command. But if we do use the appropriate command, we're going to have no problems. Now, the multiply command, while its parameters are at the word level, will always return a long. There is also a divide command, and again, there is an unsigned and a signed version called divu and divs. So let's try those as well. So what we've done here is we've divided 3401 here by hexadecimal 100. But something slightly odd has happened. You can see here, this has moved along 2 digits to the right, so that this is now 34 here, but there's a 1 here. Well, what's that 1 doing there? Well, let's have a look. When we run the divs or divu command, the returned register is actually split into 2 words. The top word is the remainder, and the bottom word is what's known as the quotient, which is the successful number of divisions that occurred. So if we divide 21 by 10, we would manage 2 successful divisions of 20 by 10, and there will be a remainder of 1. And so that's what we're seeing here. So in our example here, we've divided 3401 by 100, in hexadecimal of course. The successful divisions are 34, and there is a remainder of 1. So the top word here is the remainder, and the bottom word here is the successful divisions. Now, the same is true of our division here. We've done a division of this negative number here, and so the successful divisions were CC. But again, there was an unsuccessful division of -1. And I can just prove that to you. If I change this to a 0, there will now be no remainder, and you can see that top word is now a 0. So that's how the division commands work on the 68000. Now, there is one important thing, of course, you need to bear in mind, and it's true of all computers and all computer programming, so you may well know it already, and that is that we can't divide by 0. If you imagine a cake and you have 2 people eating it, it will take half the amount of time as 1 person. If there were 4 people eating it, it will take a quarter of the time. But if there were 0 people eating it, it will take an infinite amount of time for the cake to be eaten. This is why division by 0 is impossible. And what will actually happen if we try to do a division by 0 is the processor will crash, at least on most systems. So you don't want to do that. So if there's a risk you're going to divide by a register, you need to check if that register is 0 before you do the division and deal with that in some other way. Now, as with before, with positive and negative numbers, we need to make sure we're using the right command. If we use the wrong command here, if we do an unsigned divide on a signed number, you'll see the command hasn't worked correctly. So again, it's important to make sure the commands match the data that we're working with. Now, there's one other command I want to discuss with you at this point, and it's a very odd command because it's a command you'll either never need or you'll be absolutely relying on at all times. In 68000 assembly, there is something called traps. Now, these are designed primarily to do debugging. They handle error codes and things, and they are to some extent programmable by the user, but they aren't something you're going to tend to need in a lot of cases. But on some of the systems, depending on the 68,000 computer you're working on, they're actually used for system calls. If you're familiar with the Z80, you'll know about something called RSTs. These are jumps to low memory addresses, and they are done by a command like RST followed by a number 6. And the trap command is very similar. It jumps to a low memory address, and they are numbered from 0 to 15. However, as I say, the only case you're likely to ever need them is if you're programming a system, for example, the Atari ST, where you may need them to run BIOS calls. Now, this is the keyboard scanner routine that I use for reading in the joysticks for my IM68000 program. On the Atari ST, the only way I could get the joystick to be read in was to call the BIOS and get it to read them for me. I couldn't find any direct way of doing it. And so this command here, trap13, is a function call to the operating system, and these values I've pushed onto the stack here are then read in by that function call, and the BIOS will do the work I need it. So I'm telling you about this command at this point, not because we're going to show any examples of it at this stage, but if you're rushing ahead with a system and you're trying to use the BIOS calls, you may need these commands to do this kind of functionality. So the trap command is a command that you will need in those cases, and the important thing to know is if you find some source code and you see these trap commands in that source code, firstly understand it's probably a system call, but then what you need to do is you need to go to the manuals of that system and find out what trap13 and trap14 do, because it will be different for every system. If I run trap13 on an Atari ST, it might call the BIOS, but on a Genesis it may do nothing, or it may crash the system. So you really need to check the manuals that relate to the system you're working with if you are coming across trap commands in example code. So that's really everything I wanted to discuss in this lesson. We've gone over quite a lot of code, and at this point I think you know quite a bit about the system. We've understood now that the basic mathematics commands, we've understood how the jumps work, and we know how to use the stack. There are some other things we need to cover. The next big one is going to be working with bits. We often need to work at the bit level with our mathematics, and so we're going to discuss that next time. Anyway, I hope you've enjoyed this lesson. Thanks for watching, and goodbye.